Yeah. Is this, do you want this here? This is sort of awkward.
This is what for? What this is for?
I have no idea what it's for. I'm going to move it off to the side.
It's an obstacle.
You might not be able to. If you can give it an orientation, then that's exactly what it means for those two integers.
Okay, so let's continue. It's my pleasure to welcome Kazushi Kanoda from University of Tokyo, who will be giving us a couple of lectures on some organic materials that may be quantum spin liquids. So this is something that Leon Belenz mentioned a little bit in his last lecture, but now we're going to hear a lot more about it. So welcome.
But maybe before you
Oh right. Sorry. One announcement. I was going to say this first, but I forgot. Remember, there's a poster session tonight. So it's going to be the same routine as in previous weeks. So we'll have poster talk here at 6:30. 1 minute advertisement for your poster, and then the poster session will be up on the 11th floor as before. So please, if you're presenting, please go and put up your poster. The best time would be in between the afternoon lecture and dinner. So anytime after 3:30, when the afternoon lecture is over, you can go upstairs and put up your poster. It's going to be the same as last week. All the posters will be in the same room so that nobody's stranded off in the other room. There was some discussion about what to do, but we think it's better to have all the posters all in one room. Yeah, so it's going to be the same as that.
Yeah, just one more comment. So you see the suspicious face around. It's actually not an imposter.
All right.
Both organizers here, Jason and Lisa,
Right.
they join us. So welcome, Jason.
Okay, so with no further ado, let's hear the lecture.
Thank you, Mike. It's a great pleasure for me to give a lecture here. I'm working in the field of the organic materials. So this lecture, I'd like to talk about some experimental signatures and the physics behind it and organic materials. And maybe the textbook is available, or I've just posted the review article to the archive. Maybe this review article is available in archive. And before going to the lectures, let me introduce myself. I was born near Sendai. This is the Japanese island. It's a main island, the Hokkaido island here, the Shikoku Island and Kyushu Island. I was born here, and I graduated from Tohoku universities with nuclear engineering major, and I got a PhD from Kyoto University, and I got a job in a private university in Tokyo. The name of the university is Gakushuin University. Maybe not so familiar, but this is a very unique university. This is emperor's universities. The sons, daughters, and relatives of Japanese emperors are enter into this university here. And then I moved to the Institute for Molecular Science, which resides near Nagoya, and I moved to the University of Tokyo, and up to now, I'm working for this university. Okay, my the unique career was when I was a sophomore in Tohoku University, I was a high school baseball coach for 1 year, but I fired because of no wins. Only 1 year. Okay. Let's remind the heart of the condensed matter physics. Okay, that is the understanding of low energy state of the nucleus and electrons assemblies. Okay, let's take 3 kinds of the simple atoms: the hydrogen, helium, or lithium. At high temperatures, all of the let's imagine the many number of the atoms are confined in some vessels, and then if the vessels are at high temperatures for 1,000 kelvins or 10,000 or several thousand Kelvin, in that case, all of the 3 assemblies are plasma. Okay, the same state. However, if temperatures is decreased, in that case, the binding occurs, namely atom. And then finally, at low temperatures, the assemblies of the proton and electrons are condensed into the insulating solid. However, in this case, the assemblies are condensed into the fluid, even at 0 Kelvin. And in this case, the ground state is a metallic solid, not insulated, and then the 3 electrons per molecule, per atoms, but 2 of 3 electrons are bound in this nuclei, but 1 electrons out of 3 are superconductor. So, okay, studying elements is not so different, in my opinions. Only the difference as and a charge 1, 2, 3. But if these particles are assembled, many particles assembled, and then at low temperatures, the many qualitatively different emergence occurs. Yes, this is the interest in condensed matter physics, I think. The point is the interactions. Interaction gives the different emergence. Okay, the other important ingredient, I think, is the quantum nature. Okay, let's think about the assemblies of electrons. Okay, if they are not interacting, in that case, each electrons moving as a Bloch wave, and the assemblies are characterized by the Fermi velocities and the Fermi energies. Okay, so non-interacting electrons from the Fermi surface, but the Fermi surface is essentially a degenerate state. But the degenerate assemblies are very unstable against any kind of interactions or some forces. So many kinds of the instabilities occurs in Fermi degenerate gas or liquid. If this dimension of the electronic system is 1 or 2, in this case, the density wave occurs, charge density wave or spin density wave, or the electron interaction, short-range interaction is strong. In that case, the molten insulator occurs, and in other cases, the Wigner crystal occurs, or the interaction is attractive. In that case, the superconductivity occurs. The resistivity is infinite in these states, but in this case, the resistivity is vanishing. So completely different states, but the heart of the phenomena is the same, I think. It's instability of the Fermi surface. Okay, so we can enjoy a variety of the emergence and interacting electron systems. So the spin liquid is one of them, I think. Okay, so this is the content of my talk, or my lecture. First, I talk about the fundamentals of organic materials. Some time is devoted to the fundamental aspects, fundamental features of the molecular materials or organic materials. And then I'd like to talk about the correlation, electron correlation in organic materials. And here, I'd like to show you some correlation-induced phenomena, metal insulator transition or superconductivity, unconventional superconductivity, and so on in molecular materials. And I moved to the spin liquid issues and triangular lattice organic materials, and where we can control fluctuation and correlation, and sometimes we introduce disorder, or now doping a spin liquid is available. Okay, and if there is time left, I'd like to talk about the electron correlation effect on the massless drug fermions and organic materials. And the finding is the Dirac cone reshaping and emergence of the ferrimagnetism in massless drug fermion systems. Okay, the first chapter, molecular materials and its electronic structure. So the keywords is the variety of lattice structures in organic materials. And the important concept is the molecular orbital. This is very important. So you can you do not need to go to the atomic orbitals. The molecular orbitals enough to think about the physics going on in the molecular materials, organic materials. And it's because of the simple band structure in K-space. Okay, and the molecular materials are very highly compressible. So by pressure, you can easily tune or easily vary the material parameters. For example, the band width or the anisotropy of transfer integrals or the strength of correlation, electron correlations. Okay, that's the keywords. This is the comparison of the inorganic solids and organic solids. It's a very simple schematic. Inorganic solids, essentially the spherical atoms are assembled and like this, very simple structures. But in organic solids, the structure seemingly very, very complicated in real space because the organic molecule is usually planar molecules and low symmetry, and so in the assembly of such a kind of the anisotropic molecule gives a very, very complicated structure in real space. Okay. So this is the typical examples of the organic molecules which give the metal insulator or metal or spin liquid or superconductor. All of the molecules are very similar to each other. It's a planar, and then the length, the long axis of the molecule is maybe 1 nanometer in length, and in the 3.3 nanometer in width, okay, and nearly all of the molecules are planar. Okay, very similar, but you don't remember the exact name of the molecules. It's abbreviation, but TMTSF and BDTTF is a long, lengthy name, but even this is abbreviation. For example, this is the bis ethylene DTO tetra tiafluorine. Oh, I could do that. Okay, so very long name. This is abbreviation. Anyway, maybe please remember that the molecule is a planar, and then 1 nanometer length and 0.3 nanometer width. It's a very flat molecule. Okay. The interesting properties of the molecular materials is a variety of the molecular arrangement, even and the same compositions. That is a very prominent feature of the organic materials. For example, in copper materials, the copper forms a FCC structures, but you can change the structure to BCC or HCP or any other structures. But with organic materials, we have a variety of molecular arrangements. For example, we denote this type of the molecular arrangement is alpha. This cartoon, this schematic shows the molecule is perpendicular to the screens. It's a planar molecule. It's like this. And in the copper type materials, and so the molecule forms a strong dimer, and the dimer forms such a kind of checkerboard arrangement. And I want to stress that even with same composition, the molecular arrangement are various, like this: alpha, beta, theta. This is some example. Maybe the material BEDTTF2I3 has a 10 and more structures. So the property is also various. And for example, please compare the properties of two materials. This is ET materials, BEDTTF compounds, and the beta type arrangement, the theta type arrangement. Okay, but in these materials, the superconductivity occurs at low temperatures. However, in the theta type molecular arrangements, in low temperature electron crystallizes. The Wiener crystal occurs. So insulator and superconductivity occurs, and the same composition. But the difference is only difference is the molecular arrangement. Okay, so bandwidth and the Fermi surface changes. So the kind of instability is also varied. And the attractive interaction wins, but in this case, the long-range intersite Coulomb interactions wins, and being a crystal is a ground state. Okay.
Quick question.
Yes.
Can you control which of these structures form?
By pressure, for example. One method is to use to change the organic solvent in crystal growth. It's the type of the crystal depends on the organic solvent. So that is one method. Yeah. Or temperature or other parameters is effect has effect on the generating the different crystal. Yes. Yeah. This is a very the imprint structure in the conducting layers. But this material has consists of the two molecular species, ET molecules and then I3 molecules. And the I3 forms a sheet. So this is a layered structures. ET molecule and the I3 molecule, the ET molecule. So like a high-tensile cuprates like this. So this is the conducting plane. Okay, let's take a look at the structure, electronic structure of these molecular materials, and it's an individual, the family, and the society maybe like this. And the electronic structures, the the molecular orbital is formed, and an important point is this is the energy and the molecular orbital, and from the bottom. And this is the highest occupied molecular orbitals. Electrons are occupied, the molecular orbitals are occupied from the bottom by electrons, and then this is the highest occupied molecular orbital. This is abbreviated by HOMO. And then next molecular orbital is a LUMO, lowest unoccupied molecular orbitals. So important point is this molecule forms a solid like this. In this case, in many cases, the electronic band forms within in each molecular orbitals. No mixture. That's a very important point. If the band structures, band width is very, very wide here, so in that case, the electronic band consists of the several molecules. But in many cases, the band structure calculation shows that in each band originates from only one molecule. So in this case, the conduction band comes from the HOMO orbital. So you do not need to go to this individual molecular atomic orbitals. You should watch only the molecular orbitals, only one orbital per molecule. That is a very important point to enjoy the physics of the organic materials. Yes?
What's the typical energy spacing of?
One electron volt, 1 or 2 electron volt. It depends on the molecules, but this is a typical energy scale. Okay, later I'd like to show some examples of the energy splitting.
About the bandwidth of these bands?
0.5 or 0.3 or less than 1 electron volt. Okay, so yeah, the important point is the molecular orbital is a minimum entity for electrons, and no need to look into atomic orbitals in a low energy scale. That is the important point. Okay. Yes. Yeah, in some cases degenerate, but in many cases non-degenerate in a case. So it's a very simple. So in organic materials, it's a situation is very, very simple and non-degenerate, and no spin-orbit interaction, because the constituent elements are carbon and hydrogen, very, very light elements, so very low Z. So non-degenerate, no spin-orbit interactions, so no complications. So no topological insulated. Okay, and what is the molecular orbital? And it's a very the simplest example is the hydrogen molecule, and hydrogen molecules okay, like this. So this is a hydrogen. The 1s atomic orbitals and hydrogen atoms, and 2 hydrogen atoms are nearby each other, and the degenerate 2 1s orbitals split into the bonding orbital and the anti-bonding orbitals. And the bonding orbital is like this, and in between the 2 nuclei, the atomic orbital or molecular orbital has a finite probability, but in anti-bonding orbitals, the vanishing in between. And this is the very simple atomic orbital. So, okay, let's think about the degenerate case. This is the non-degenerate case, because in hydrogen atoms only 1 s orbital, so non-degenerate case. Okay. Organic materials consist of the many hydrogen atoms. So we have to consider the degenerate orbitals. And carbon case is that is the p orbitals, 2s and 2p orbital. Yeah, 2s and 2p orbitals. So 4 degenerate and isolated carbon atoms. Okay. okay, let's think about the how to construct the molecular orbitals in such a kind of a degenerate case in the following steps. First, okay, let's think about the hydrogen atoms, your hydrogen atom, okay? And let's consider or imagine, oh, no. Sorry, this one. And different atoms are approaching you, okay? Approaching you in that case. So the four degenerate orbitals are hybridized within the atoms, okay? And this is the x-axis. Okay, so the y-axis or z-axis is perpendicular to this the axis. So the py and pz is not so affected by this alien atoms. But the px and s orbitals are seriously influenced by this approach of this alien atoms. So in the first step, the intra-atomic hybridization occurs. Intra-atomic hybridization means that the sp hybridization, like this, sp hybridization, and here. But the py and pz is not so strongly affected here. And when the neighboring atoms get closer and closer to the carbon, in that case, some chemical bonding occurs. The chemical bonding means that it's exactly the same as the formation of the hydrogen molecules. So bonding and anti-bonding. Okay, that's all about the chemical bonding of the carbon around the carbon atoms. Yes.
About chemistry, you're having the hybridization between S and PX.
S and px, yes.
But if you look at this configuration, let's see that animal interaction.
I cannot catch your question.
So my question is,
Yeah.
this
Yeah, px orbital is like this, s orbital here, and then the two atoms approaching here, approaching like this, and then so
I was thinking about angular momentum calculation. We have this kind of
angular moment.
the angular momentum along the horizontal line should be observed.
Horizontal line. So you mean that along this axis? I don't know. But anyway, yeah. Your question is related to this SPX is degenerate. It's some associated with some conservation of angular momentum, maybe. I don't know.
Is that the reason why it couples only to PX?
Only to PX pair. So
So you cannot couple to P1 and P2?
this is angular momentum is preserved, yeah, degenerating in this case. But this is one axis, so but no angular momentum. Yeah, zero, yeah. Okay. Anyway, in the final step, this hybridized orbital intra-atomic hybridized orbitals split to the bonding and anti-bonding. This is the chemical bonding. Okay, the same thing occurs in a four-way coordination of the alien atoms like this, carbon atoms, and then, for example, please imagine the hydrogen. For hydrogen approaching from the tetrahedral angle. In that case, this is a methane case. It's a methane case. In that case, the hybridization occurs sp3, okay, and then all of the molecules, all of the atomic orbitals are hybridized in four directions. But this four direction is equivalent. So even when the hybridization occurs, the four hybridized orbitals are degenerate like this. And hydrogen atoms, when hydrogen atoms approaches very, very close to the carbon side, in that case, the hydrogen molecule-like chemical bond forms. So bonding and anti-bonding orbitals occurs. Okay, such a kind of the profile of the molecular orbitals occurs in the methane and diamond and silicon and the germanium. So the origin of the semiconductors and the semiconducting gap corresponds to the bonding and antibonding gaps. Okay, this is the example of the molecular orbitals of CH4 methane in the methane case. Many molecular orbitals. That is the molecular orbitals. But this is still very highly symmetric because the carbon and tetrahedral coordination has a good symmetry. So the lowest molecular orbital is non-degenerate, but and other three orbitals are degenerate. In our case, in organic materials, the molecule is planar, but the symmetry is very bad. So this means that the degeneracy is lifted like this. It's a molecular orbitals. And this is a highly occupied molecular orbitals, and the lowest occupied molecular LUMO, the higher LUMO. So the level spacing is 1 electron volt or 2 electron volt like this. So, and this is a different case. This kind of molecules has such kind of the profile of the HOMO and LUMO like this. So anyway, the molecular orbitals are extending over the molecules, and this plays a similar role of the atomic orbitals in, for example, copper. So molecular orbital is all about the organic materials. Okay, let's see the bond structure. This is the bond structure calculation of the 10 Kelvin organic superconductors. Okay, please take a look at this. And this is the first principles calculations. And this level corresponds to the HOMO, and this is a LUMO, and this branch corresponds to the originates from the HOMO -1. So well separated. So this is the conduction band. The conduction band comes from the comes solely from the HOMO orbital. So this guarantees that you should think only the HOMO and the HOMO band to think about the electronic structure. For example, if you construct the Hubbard model or some theoretical model, the first approximation is the band structure. You can start from the band structure of this HOMO orbital. So you can easily calculate the band structure by tight binding approximations based on these HOMO levels. So the band structure is very simple. This is Fermi surface. Okay, this is Fermi surface, and this is Fermi surface. Okay, the same one. Okay, please take a look at this one. This is a first brilliant zone, and this is the Fermi surface. Is a part of the Fermi surface is folded here, but essentially the Fermi surface is circular. So very simple two-dimensional cylindrical Fermi surface results from the tight binding calculations of the HOMO orbital. So in real space, the molecular materials seems very complicated. So, but in K space, it's very simple. That's the important point of the molecular orbitals. Okay, let me again repeat the importance in enjoying the molecular materials. That is the So this HOMO molecular orbitals plays the same role of the d orbitals and copper. Okay, this is the first approximations. And let me summarize the properties of the molecular materials. They seem complicated structure in real space, but in K space it's very simple. And in many cases, the no orbital degeneracies, and then negligible spin orbit interactions. So in some cases, not so interesting, but in some cases, very simple. So it's a trade-off, depending on the physics. And additional important point is the highly compressible natures. So you can easily control the material parameters by applying pressures. Maybe roughly saying the pressure effect 10 times larger than the inorganic materials. It's yes.
So in your previous slides, you mentioned that we should try to
Yeah. You're asking the U. In this case, U is very large, but in this case, U is very small. It's roughly saying the one order of magnitude different. Yeah, but the boundaries is also one order of magnitude different. So everything is one order of magnitude smaller than the inorganic materials. For example, maybe magnetic ordering and lantern to copper 04. It's the matter mode insulating phase of the cuprates has shows the ordering 200 or 300 kelvins, but in organic materials 20 or 30 kelvin. And TC is 100 kelvin in cuprates, but in our case 10 kelvin. So all of the energy scales is one order of magnitude lower in organic materials. Yeah. Yeah. 2 orbital. It's HOMO. Yeah, only HOMO. One molecule, one orbital. Okay. This is the unit cell contains 4 molecules. This is copper type molecular material, so that is a reasonable for the 4 bands. Okay, I'm moving on to the next chapter, the electron correlation in organic materials. So to say, the all-in-one system from physics. Okay, this is the I pick up the typical 4 materials and the investigations in the organic materials community. This is the very famous materials, TMTSF2X. This is the first organic superconductors, which was the superconductivity was discovered 1990, yeah, maybe a quarter of a century before. And this is the first 10 Kelvin organic superconductors, layered materials. And this is also layered materials. It's charge ordered materials. And this is the alpha type arrangement. So the essential difference between these materials are and molecular arrangement. The molecules are different, but the difference in the molecular structure doesn't matter. The important point is the molecular arrangement. Okay, so this is the band structure calculations of each materials. In these materials, you can imagine that the strongly one-dimensional character. Okay, this is the TMTSF molecule is like this. And this planar molecules stacking in these directions. So the conductivity is very, very high in these directions, but conductivity is low. The ratio of the conductivity is roughly 1,000. It's a very strong one-dimensional nature in these materials. And the Fermi surface is like this. So reflecting the one-dimensional character of the structures, the open Fermi surface with one-dimensional nature emerges like this. And these materials, as I said before, the Fermi surface is cylindrical, and this material is also cylindrical. And this material is a semi-metal, so electron pocket and hole pocket a pair of the hole pockets and electron pockets. Anyway, very simple Fermi surface results from the tight binding calculations or first principles calculations of band structure. However, in reality, the ground state is not metal for all of these materials. And this is a pressure, okay? At ambient pressure, for example, this material is a spin density wave transitions. And if X is bromine, in that case, the antiferromagnetic order. Or if X is PF6, in that case, the spin pulse state is a ground state. But if you apply pressures, the metal emerges. And at low temperature, superconductivity appears. Okay. For in the second example, the ambient pressure is not insulated, but under pressures and more transition occurs, and then metallic state appears, and at low temperatures you have unconventional superconductivity. They're probably of D-wave nature. And for these materials, at ambient pressure, also shows an insulator and charge-ordered insulators. But at high pressures, the charge-ordered insulated is changed to the superconductivity. Now the nature of the superconductivity is one of the hot topics in these communities. The superconductivity neighboring charge-ordered state. So charge fluctuation is related to the superconductivity or not is the focus in the superconductivity research in organic materials. Okay, and the first example, at ambient pressure, again, this material again shows the charge ordered state. But if you apply pressure, the charge order suppressed, and then massless Dirac electrons emerges. So this massless Dirac electrons is strongly correlated because the neighboring phase is a charge ordered phase. So we have now under pressure strongly correlated massless Dirac fermions. So if I have some time tomorrow, I'd like to touch the Coulomb electron correlation effect on this massless Dirac electrons. It's a very recent result. Okay, anyway, by this page, I'd like to emphasize that in organic materials, electron correlation plays a vital role. Band structure calculation gives a metal and Fermi surface, but most of them are insulators at ambient pressures. So this is a clear evidence that the electron correlation is very, very strong in this material. But I have to say, related to the questions, the on-site Coulomb interaction or inter-site Coulomb interaction is not so strong compared with the inorganic materials because the molecular orbital is extended over the molecules. The important point is the bandwidth is also small. So competition between the bandwidth and the on-site Coulomb interaction, in other words, kinetic energy of electrons and electron Coulomb interaction is comparable. Magnitude of these quantities are very, very small compared with the inorganic case, but the competition is the same. So that's the reason why we have so many correlation-induced insulators in organic materials. Okay, a kind of sociology of the electronic systems. So the spin liquid emerges from this family of materials. So from now on, I'd like to focus on these materials, the Mott transition systems. Okay, Mott transition. This is a very introductory or primitive diagraph to explain the Mott transitions. It's a green circle represents the molecules. It's in the half-fill band case. In the case, each molecule hosts one electrons on average, and the important point is the kinetic energy and the Coulomb energy, which wins. And the kinetic energy wins like this. In that case, the electrons propagate as a Bloch wave. So it's a wave nature wins. But it's the balance is reversed. In that case, the Coulomb energy is Coulomb energy wins. So electrons are localized. So particle nature emerges. So the electron's duality, namely particle nature and wave nature, appears depending on the balance of the on-state Coulomb interaction and the kinetic energies. That is a mode transition. Okay. So in this limit, the bandwidth or kinetic energy is much, much greater than U. In that case, the system is metallic. It's a very, very understandable situations. But in the opposite limit, it's also very easily understandable. Its electrons are localized, the motor insulator. It's metal and the motor insulator. So in two limiting cases, it's this situation is quite easily understandable. So the theorists usually employs the Hubbard model to understand this the landscape of the phase space spanned by the U and T or U and W's, and then the two ways of representations is if you take the Bloch wave as a basis, in that case, the Hubbard Hamiltonian look like this, and if you choose the one-year wave functions, in that case, the Hamiltonian is expressed like this. So you can choose either of these representation. For example, the weak correlation. So the second term is very, very small. In that case, this first term is a unperturbed Hamiltonian. So, but in this case, it's off diagonal. So in that case, you should choose this one because the unperturbed Hamiltonian is diagonalized here. So this is this off diagonal term is treated by perturbatively. So in this case, this term is a perturbation, and then scattering rate is easily calculated like this. So the scattering rate is proportional to the square of temperature, roughly speaking, temperatures. In 2D case, strictly speaking, that there is a prefactor, logarithmic prefactor, but this prefactor is very temperature dependence is very, very weak. So in many cases, experimentalists neglect this one. So in practically in two-dimensional and three-dimensional cases, the temperature dependence for resistivity is proportional to the square of temperature. This is the manifestation of the electron correlation in the weakly correlated regime. And in the opposite case, in that case, this is the main term, this is a perturbation term. So you should choose this one-year function representation because this is diagonalized. Okay, so you can treat this first term as a perturbation, and then this Hubbard model is reduced to the Heisenberg model, as is well known. So in the motor insulating states, it's an antiferromagnetic state is stabilized in antiferromagnetic insulators. The point is, and the difficulty occurs in the intermediate state, namely bandwidths in a situation where bandwidths and the on-site Coulomb interaction is comparable. So this in such a situations, the only numerics is a effective method to do research in this region. So several or many calculations of the Hubbard model in this intermediate region is published. And for example, this is this are only two examples. This is the result of the path integral renormalization group method, PIRG, abbreviated to PIRG, and this is a cluster DMFT method. And roughly, these two phase diagram gives a similar profile. Namely, this is the T prime over T and E over T. Oh, okay. Sorry. This calculation assumes that this lattice geometries and square lattice T, transfer integral with transfer integral T, and then this diagonal transfer integral T prime also present. And they changes that the ratio of T prime over T as a parameter. And then U over T is a strength of correlation, correlation strength as a vertical axis. So if T prime is 0, in that case, the lattice is scale lattice. And T prime is T, in that case, the lattice is a triangular lattice. And T prime is infinite, in that case, one-dimensional change. So this parameterization treats the weakly coupled one-dimensional change and triangular lattice and the scale lattice as a function of the T prime over T. Okay, and so this is the metal and mott insulator, and in this phase diagram, it's a superconductivity appears. So at present, please neglect this superconductivity. This is the mott insulating boundary here. So you see the mott transition, the boundary, mott transition boundary, namely the critical value U over T depends on T prime over T. It's for example, in the limit of the square lattice, in that case, it's the U over T, the critical value U over T is vanishing. It's a very nesting is good in this case. So infinitesimal U gives mott transitions, mott insulators. But if the frustration is increased in the triangular lattice, in that case, the mott transition is difficult to have mott transitions up to enough large value, up to large values of the U over T. Okay. But this profile is roughly reproduced. Okay. Anyway, to study the intermediate regions of the mott transitions, the numerics is a very good and maybe only method to study the practical phase diagram. Okay, again, I'd like to stress and show that the variety of the molecular arrangement in organic materials, alpha, beta, theta, beta prime, kappa, lambda. And this is the imprint structure. All of these materials have a layered structure like this. This is the ET molecule, BEDT molecule. These molecules forms one monolayer like this as a conducting here. So these ET molecules are arranging perpendicular to the screen. So two-dimensional arrangement like this. So, and this X plays a role of the insulating block layers, like the block layer in the high tissue cuprates, the insulating layers. So the X, many kinds of molecular species as X, and X like this. It's one monolayer. It's insulating and non-magnetic. So only spacer. But the conductivity ratio typically is 1,000 for all these materials. It's a conductive in this layer, in these directions, two-dimensional directions, but in these directions, it's a very bad conduction, electric conduction. Okay, spin liquid emerges from this kind of the molecular arrangement, which is abbreviated to by a copper type molecular arrangement. As I said, this ET molecule forms a dimer, and this dimer forms a checkerboard pattern in these conducting layers. Okay, the interesting point is this dimerization is very strong with respect to the molecular orbitals, because the molecular orbital is extending perpendicular to the plane, because the PZ orbital is a main contribution to the molecular orbitals. So PZ orbital means that this is the ET molecules, and PZ orbital is extending perpendicular to the layer. So if the molecule, even if the molecule approaches in these directions, the overlapping is very small. But in these directions, the overlapping very effective. So this dimer has a very strong hybridization between the constituent two molecular orbitals, homo orbitals. So you can regard this dimer as a one supermolecule. Okay. So this dimer is not a two molecules; it's a one supermolecule. Okay. So if so, this structure is modeled to the anisotropic triangular lattice. One dimer plays a role of the one lattice point. Okay. And transfer integrals, there are two kinds of transfer integral, T and T prime. Two kinds of transfer integral characterize the lattice, like this. And additional important point is the band filling. And X is the valence is -1, namely 1 electrons are absorbed from these ET layers. So this is -1. This means ET2 has a 1 hole +1. So this dimer, one dimer has a 1 hole. It means one lattice accommodates 1 hole. Okay, so this is the half-filled band, effectively half-filled band. So this materials is modeled to the anisotropic triangular lattice with a half-filled band. Okay, and you can change the molecular species residing in the insulating layers, and many molecular species. Cu2CN3. It's a lengthy name, but many molecular species. But by changing molecular species, this T and T prime and U over T, namely material parameters, are also varied. That is an interesting point. This is rough estimations. Later, I'd like to show you how to estimate U. It's a very simple method. It's available. Anyway, by changing the anion species, the U over T is also changing. The highly correlated, and correlation is very small in this case. And T prime over T, this is the degree of the fluctuations, is also largely changed, varied, depending on the molecular species in the anion layers. And these materials is a nearly triangular lattice, and indeed, these materials host a quantum spin liquid, which is explained in detail later. But these materials, it's less fluctuated materials. The symmetry of the lattice tends to be to the square lattice. Okay. But this is a molten insulator, but the antiferromagnetic ground state is a real ground state. But the important point is that these two materials are molten insulators, but other materials are metal. So this means this family of materials on the verge of the mode transitions. So U and W is comparable. Okay. And in reality, this is the resistivity data of this family of material. Some materials is insulating, and some materials are metallic and superconducting occurs. And okay, important point. Interesting material is this one. This one. This is just on the verge of the mode transition. Okay, so this is the isotope effect. Usually, isotope effect is a very subtle effect. For example, the small change of the TC or small change of some transition temperature. But in our materials, the isotope effect it causes metal insulator transition or superconductor insulator transition. It's a very huge. That is because these materials resides on the verge of the mode transitions, and by replacing hydrogen by deuterium, in that case, the molecular arrangement slightly changed, and the bandwidth is slightly changed, and then the 10 Kelvin superconductors is changed to the mode insulators by deuterations. So this is the clear evidence that this family of materials reside just on the verge of the mode insulator, mode transition. Okay. So this is the rough phase diagram of this family of materials. These materials reside in the molten shredding side, and other members are situated in the metallic side. And I'd like to show you some rough estimate of the U of these materials. And okay, this is the ET dimer, and this is the energy scheme. This is the ET molecular level, and the dimerization is very strong. So the transfer integral TD, then it's a kind of the hydrogen molecules. So by this intra-dimer transfer integrals, this is bonding orbitals and antibonding orbitals. These degenerate orbitals split. Okay, so this is the energy scheme profile of this ET dimers. And if one electrons reside in this ET dimers, in that case, electrons here. But if two electrons come in, one dimers, in that case, another electrons comes in, but this intra-ET on-site Coulomb interaction is strong, very strong. In that case, so the two electrons are separated. It's like a Hydra-London state. So it's a two electron state. Very simple picture. Okay, two electron state is like this. Then this is a TD. So on dimer Coulomb interactions is roughly the difference of energy levels. So this is 2 TD. Okay, two electrons here, and then one electron here comes in, and then electrons here. So electrons TD and twice TD it's a rough estimate of the U dimers. And from the band structure calculations, TD is 0.25 electron volt, and band structure gives 0.4 electron volt. So it's a comparable. Twice of TD is 0.5. So this and this is very comparable. So this is this reason rationalize the emergence of the mode transition in this family of materials is a rough estimations. Okay, but more rigorous treatment is like this, and this is the one electron case. In that case, this is a rigorous result, and the one electron is residing in the bonding orbitals. But if two electrons comes in, and this means it's the exact problem of the hydrogen Hubbard model of hydrogen molecule. Okay, so this is also exact solutions, and this simplifications assumes that this level is exactly the same distance. But if U means that this ETU. In these approximations, we assume that the EUT is infinite. In that case, it's a twice of TD. Yeah.
Can you fine tune those parameters by applying stress in particular way?
Yeah. It's possible. By pressure, we use two kinds of pressures. One pressure is hydrostatic pressures, and another method is uniaxial pressures. So we can tune the variation of the transfer integrals, for example, in this direction or in other directions.
How much of percentage?
20% or 30%. Maybe in experiments, and 3 or 4 gigapascal is a laboratory, the pressure scale of laboratory. In 3 gigapascal, in that way, 20 or 30% reduced of the transfer is reduced. Yeah. Okay, this is rigorous treatment, but this is the result. Okay. Anyway, if the U is large, in that case, this is approaching 0. So the on-dimer effective U is roughly given by twice TD. Okay. So this materials spans the phase diagram of the Mott transitions as a temperature and this correlation strengths. So this is first order Mott transition boundaries. And you can enjoy the spin physics in these regions and the charge physics, namely Mott transition. And then at high pressures, the metallic phase stabilizes and the superconductivity appears at low temperature. So in each regions, many interesting property occurs. And quantum criticality of the transitions is observed recently. And the spin liquid or spin order is observed. That is the topic in my lectures. And in this regions, spin charge coupled phenomena, namely superconductivity occurs. This is the unconventional superconductivity, and recent observation experiments suggest that preformed Cooper pairs occurs up to twice of TC. It's a very, very high temperatures. It's if I have a time, I'd like to touch these topics. Such a Sitter gap and high-density cuprate is under strong debate. But in this case, no competing orders, which is different from the high-density cuprates. Even without competing orders, the Sitter gap appears up to twice of TC. So this is ascribable to the preformed Cooper pairs. Okay, anyway, in my lectures, I focus on this doped spin liquid. Spin liquid physics. Okay, and then I'd like to show you some very recent results on a doped spin liquid. A doped spin liquid is realized, substantiated in real materials. Okay, and the Mott insulating states, the charges are localized. So remaining degrees of freedom is a spins. So this is the rough sketch of the history of the spin physics. The Heisenberg interactions and the spins are located in the scale lattice. In that case, this Heisenberg interaction gives a null state. But interestingly, Landau was very suspicious about the realization of the null state because the spin 1/2 should exhibit quantum fluctuations. However, the Newton experiments prove that the null state is the real ground state. So Landau's opinion was wrong. But the 1973, Anderson proposed that the quantum fluctuations which Landau has insisted can be vital and on the triangular lattice. And some spin liquid state, some kind of spin liquid state may emerge. And many kinds of the triangle-based lattice, the triangular lattice, and conglomerate lattice, and hyperconglomerate lattice, and the pyrochlore lattice. Okay. And yesterday, Leon gave a lecture on these topics. The Anderson's idea is based on it's a benzene. The electronic structure of benzene is a superposition of the two states. It's a resonating state, and this finite size resonating state is generalized to the infinite size, and the Anderson's RBB state. Okay. However, the numerical studies on of triangular lattice Heisenberg model gave solutions that is 120-degree Néel order in maybe 1990. So the people seeking for spin liquid are disappointed. So the search for spin liquid seems to the end. But no, because the Heisenberg model is one specific model of the interacting spins, but in real materials, many other interactions may be present beyond our scope. So in reality, the organic materials shows spin liquid materials, which is opposed to the numerical calculations of the Heisenberg model. Okay, the materials like this is this. As I said, this material, kappa type of organic materials, this materials imprint structure is modeled to the anisotropic triangular lattice. And please pick up now. I am picking up two materials, two mode insulators at ambient pressure. One is the nearly triangular lattice mode insulator. The other one is a deformed triangular lattice. It's a big, seriously deformed, and deformed toward square lattice. And this is the anti-ferromagnetic mode insulator. This is a spin liquid. Okay. Okay, let's see the magnetism and compare the magnetism of the two materials. And okay, I'd like to show Nmr experiments. So before showing the experimental data, I'd like to introduce some fundamentals of Nmr. First, use this biograph. Okay. In our Nmr experiments, the nuclear spins residing on the center of the carbon-13. But natural abundance of the carbon-13 is only 1%. 99% of the carbon is carbon-12. Carbon-12 does not have spins, nuclear spins. So to do carbon-13 Nmr experiments, we have to synthesize the molecules with carbon-13 isotopes in these particular sites. Okay, so we synthesize carbon-13 enriched molecule, and the molecular orbital like this. So electron spins is extending over this molecular orbitals, and carbon-13 spins like this. Yeah. So carbon-13 spin sees the electron spins. That's the Nmr, and okay. So this the pink colored circle stands for the molecular orbitals. So electron spins are extending and in this circle, in this fields, okay? And then nuclear spins fills the local field generated by electron spins. And that is the additional field which nuclear spin fills. The major field is the applied field, H0. H0 is a typically 1 Tesla or 10 Tesla, very big field. And then under this field, electron spins are polarized in the paramagnetic state or superconducting state. So this electron spins gives an additional field to the nuclear spins. This additional field is very small compared with H0. Okay, please remember that the electron spin and nuclear spins fields are two kinds of the field. One is applied field, and second one is additional field. This additional field is very important to know the state of the electron spins, electronic state. Okay, if you apply magnetic field to these systems, the nuclear spins with spin 1/2. For example, carbon-13 has a spin 1/2. In that case, the Zeeman splitting occurs. Okay, and this Zeeman splitting level is when splitting is equal to the H/omega, the externally irradiated RF field, the quanta. In that case, the resonance occurs. So the resonance frequency omega 0 is equal to the gamma n. Gamma n means the gyromagnetic ratio specific to the nuclear spins, and multiplied by magnetic field. This magnetic field is a total magnetic field, which nuclear spin field, applied field, and additional field. Okay, so if you observe the NMR signal absorption, in that case, for example, if you vary the frequency omega, in that case, some resonance occurs when omega is equal to this values. Then, if there is no additional field, signal should appear omega 0, but some shift occurs due to additional magnetic field generated by electron spin. That is spin shift or night shift. This shift is proportional to the spin susceptibility. Okay, so this shift of NMR line probes the spin susceptibility from the microscopic level. Okay, so this shift probes the local field generated by electron spins. And okay, in other words, the night shift usually denoted by K, because night, the first character, is spin susceptibility. Spin susceptibility is is called uniform spin susceptibility. And this is a coupling constant between electron spin and nuclear spin. It's a coupling constant. And this K is this one, this shift. And in Nmr experiments, we also measure Nmr relaxation rate. Nmr relaxation rate means that the nuclear spins are in equilibrium state. The nuclear spins, up spin, down spins, are distributed following the Boltzmann statistics. But if you apply RF field, the transition occurs, and then the spin temperature is varied, is controlled. For example, the very infinite temperatures. And then RF field is switched off. Then the spin distributions relax to the equilibrium state. This relaxation time is T1. And this inverse 1/T1 is relaxation rate. Relaxation rate is characterized by the fluctuating field. This is a static field, maybe uniform field. This is the spin fluctuation, characterized as spin fluctuations. This is the fluctuation, so the square of the coupling constant, roughly, it's okay. Many prefactors, so roughly, and summation of the Q. And many the spin fluctuation with different wave vectors contribute to the Nmr relaxation rate. And for example, roughly Q and chi. In that case, chi double prime. Chi double prime means the contributed dissipation, energy dissipations. It's chi double prime Q. In free electrons, in that case, this does not depend on Q. In free electrons, non-interacting. Is constant. So the summation is taken over the fast brilliant zone, so it's a constant. It does not depend on temperatures. Sorry, 1/T1T. Sorry, 1/T1T. So in free electron regime, the 1/T1T equal constant. This is called the Collinger relations. Maybe some of you heard the name of the Collinger relations. But in spin fluctuations is a vital in a particular way. For example, anti-ferromagnetic fluctuations is strong. In that case, it's like the profile is like this. So anyway, the integration is different from the free electron case. But in the simple case, even in the correlated case, this summation is essentially a constant in the simple cases. So 1 over T1T equal constant. This is a Collins relation holds in uncorrelated and correlated case in many cases. Okay, in metallic states. Okay, with this in mind, please take a look at the experimental data. This is the NMR, proton NMR spectrum, and this is the magnetic susceptibility, spin susceptibility of the two materials. Okay, this is the less frustrated case, the deformable triangularis. It's a weak temperature dependence, but you see abrupt jump of susceptibility around 30 Kelvin or 25 Kelvin. And this is a clear indication of some magnetic transition occurs. However, the triangularis material does not show any sharp anomalies down to the lowest temperatures, 2 Kelvin in this case. So there seems no magnetic transitions and spin susceptibilities. Please take a look at the Nmr spectra. Okay, this less frustrated case, the magnetic transition occurs around 30 Kelvin. So the NMR line single peak at high temperatures. So this peak 156 something hertz. This corresponds to the external magnetic field. In this case, proton NMR coupling constant is very, very small. It's very, very small. So in the paramagnetic state, its night shift is not resolved. It's very small. However, the spins are ordered. In that case, the magnetization is very huge. So this shift is resolved. So this is the clear indication of the magnetic ordering. Below 27 kelvins, line splitting. This means that this is an applied field, and some nuclear spins feels additional positive field. Some other nuclear spins feels additional negative field. Some spins feels very small positive field. Anyway, this is the generation of the internal field. Yeah.
Just said the night shift is proportional to the susceptibility
Yeah.
back to 0.
Yes.
The water state is a candidate.
Yeah. And in this case, it's an ordered case. This is a metallic case.
Oh,
I'm sorry. Yeah. In the ordered case, it's staggered. Magnetization is staggered. In that case, it's This is long statement. Yeah. Yeah. So okay, magnetic ordering occurs. This is a clear indication. However, please take a look at this spectrum. No change down to 32 millikelvin. But this doublet, the double peak structure, this does not matter because this is due to peak doublet dipole coupling between the two carbon atoms. Okay, two proton atoms. The proton is neighboring. Two protons neighboring, and on the edge of the molecules. So this dipole coupling gives a splitting. This splitting depends on the magnetic field directions. And in some directions, this splitting is vanishing. This angle is called the magic angle. But in these experiments, we are lucky because the field angle is just on the magic angle. So no splitting. But in this case, the peak doublet is clearly seen. But this splitting is due to the nuclear dipole interaction, not related to the electronic state. So the important point, and point is this spectral shape changes or not when temperature is decreased. So you see the spectral profile does not change down to 32 millikelvins. 32 millikelvins is 4 orders of magnitude lower than these exchange interactions. So from these experiments, we concluded the quantum spin liquid is realized in these materials. And I'd like to remind you that the one significant point is the temperature dependence of the magnetic susceptibility is well reproduced by triangular lattice Heisenberg model. This is a very important point, I think, because the triangular lattice Heisenberg model gives a ground state of 120-degree Néel state. However, real ground state is spin liquid. So something happens in intermediate temperature range, because in this peak is reproduced by this Heisenberg model, good reproduction. This means that in this temperature region, some, how to say, the bosonic excitations is a very appropriate description, because the ground state is at 120 degrees of Néel orders. So this is maybe this peak is a manifestation of the short range order of the 120 degrees of short range order. So its excitations may be the bosonic. However, as I show later, the ground state is fermionic. So some change occurs and in the intermediate temperature range. So please remember that the temperature dependence of the spin susceptibilities. Okay, so the NMR relaxation rate, temperature dependence of NMR relaxation rate gives a hint to this puzzle. As I said, and this coupling constant is very, very small at proton site, because the proton is located on the edge of the molecules. So HOMO, the spatial profile of the HOMO is centered in the molecular, in ET molecule, and on the edge of the molecules, vanishingly small amplitude. So the hyperfine coupling constant, this coupling constant is very small. So to see, to look into the nature of the spin magnetism or electron spin dynamics, we have to do the carbon-13 NMR. Carbon-13 is located on the center of the molecular orbitals. So this coupling constant is large. And this is the temperature dependence of the NMR relaxation rate. So 1/T1 characterizes the fluctuating magnetic field. Okay, this is the logarithmic scale, the same data represented in linear scales. Okay, please take a look at this. And two data come from the two kinds of the carbon site. The difference is only in the amplitude of the coupling constant. So the important point is the temperature dependence. So it does not matter. The two carbon site shows nearly exactly the same temperature dependence. Okay, at high temperatures, the temperature dependence is approximated by square root of temperature, okay, like this. And this means that down to 10 kelvins. This means above 10 kelvins, the spin state is the same state, 100 Kelvin and room temperature. So as I said, that the high temperature spin susceptibilities is well reproduced by the triangular lattice Heisenberg model. So this means above 10 Kelvin, it's fluctuating. The short range order of 120 degree is fluctuating. That is a guess. But below 10 Kelvin, something happens. 1/T1T is not suddenly, gradually decreasing. So this is I think this is a crossover from the 120-degree fluctuating to a crossover from the fluctuation of the Nair state to the Flaminic spin regime. It's a guess. And at further lower temperatures, and this anomalous decrease occurs. So this is completely open questions. I don't know what happens. But anyway, this temperature dependence is power law. Okay, we should stop. I should stop. No.
We'll get into
Yeah. Okay. Okay. Well, more 5 minutes. Yeah.
not critical.
I see.
That was not my son.
Okay. So 5 minutes. Okay. Triangular lattice Heisenberg model predicts that the 120-degree Nair state, but in real materials, no such state. The spin liquid is realized. Why? That's the questions. One solution, one answer is the materials is near mode transitions. So in these situations, the spin state cannot be well described by Heisenberg model. Rather than Heisenberg model, Hubbard model is more appropriate. So this is the experimental phase diagram of a spin liquid. At ambient pressure, this system does not show spin ordering, spin liquid, and under pressure, the metal. And 140 megapascal is a relatively small pressure. So this material at ambient pressure is very close to the mode boundary. So from this phase diagram, we can say that the spin states of these materials should not be described by Heisenberg model. Maybe Hubbard model or extended Hubbard model, maybe more suitable model, I think. Okay, so many numerical studies conducted in terms of the Hubbard model, and so, but I have to say that the situation is just so simple. It's still under debate, and the early stage results, numerics, predicted the non-magnetic insulated. This is maybe spin liquid, corresponding to spin liquid. Spin liquid reside near the mode boundaries. It's consistent with experiments. And this cellular DMFT also predicts the similar phase diagram. And however, this another group predicted in triangular lattice situations, no spin liquid. It's a spiral order is stabilized, but spin liquid resides in these regions. And the idea is that in triangular lattice geometry, the 120-degree spin configurations is stabilized, even in the finite U. And in the scalar lattice, it's a Nair state, it's a collinear Nair state. So in between these two spin configurations, it's a spin configuration ordering. It's very unstable. In such a situation, spin liquid emerges. That is their claim, and based on these numerical studies. But very recently, another group reported the different results. But again, on the triangular lattice geometry, spin liquid is stabilized. So still moving with respect to the theoretical studies. So, but in experiments, we can say that near mode transitions, the spin liquid materials reside near mode transition. Okay, I like to introduce some other numerical studies. Okay, spin liquid resides near the mode boundary here, but some other theoreticians predicts that no spin liquid in triangular lattice geometries. So I'm not sure which results is most reliable in numerical studies. Okay, so the study of quantum liquid is it's difficult and numerical studies. It's not so easy business, I think. Okay, I should stop here. Okay, tomorrow I talk about the thermodynamics of the spin liquid, and then phase diagram of the spin liquid. From phase diagram, we can guess the entropy of the spin liquid. And next, I'd like to show you some disorder gives quantum spin liquid. In other words, quench the disorder induces quantum disorder. And finally, I'd like to show you some doped spin liquid. Okay. If there's some question, okay. Yes. A nail is a collinear nail state. Collinear, and 120 degrees is like such. It's a nail state is a collinear state. Yeah. Yes.
So I was actually confused because if it's a spin liquid, I would expect a shorter lifetime because quantum fluctuation of the rotation is more larger than one that
I don't know. You are saying that in quantum spin liquid state, the spin fluctuation is very, very strong?
Yeah. I mean, naively, I expect so, rather than like.
It's dynamics of the spin liquid is strongly debatable issues, I think. I don't know. But I can say that the from the Nmr relaxation rate, okay, yeah, this probes the relaxation rate, yeah, and okay, it's a power law. So relaxation rate is decreasing and slowing down and slowing down. But this is a quantum spin liquid, so it's a. But anyway, it's a. I don't know how to think about the dynamics of a spin liquid. So you mean that okay, okay, in these regions, 120 degree spin configurations is short ranged. In that case, the spin fluctuation is strong in these regions. You were saying that? This?
No, what I'm saying is, naively thinking the relaxation rate will be proportional to the magnetic nodes created by the surrounding area. With that intuition, if it's a spin liquid compared to the Neal state, your fluctuation will be larger.
Of course. Yeah.
It's a summer fluctuation, still such a fluctuation.
Yeah.
So I'll just say the relaxation rate will be faster.
In 120 degree Neal state, it's an ordered state. So at low temperatures, maybe the relaxation rate should decrease as exponential or power law. Yeah, you're right, I think. If the 120 Neal state is realized, in that case, the relaxation rate below Neal state is very steeply suppressed compared with the spin liquid, I think.
It depends on the excitation spectrum.
Yeah, I see.
Rate, which this probably isn't, but thinking in a gas spin liquid will probably go. I think that one has to be careful about associating
Yeah, gap spin liquid has a very clear consequence. It's a very exponentially dies. Yes.
Actually, just to clarify, the spins of this system come from the molecule.
Yeah. No couple, molecule. Couple. The balanced couple is +1. It's a monovalent and non-magnetic. And the spins coming from this molecule, ET2. Sorry, but this one? This one? Couple. This couple? This is insulating. Is residing insulating. Yes.
One more question. Have you tried measuring T2?
Yes. Oh, good questions. We measure T2, and the T2 is T2 is like this, and below roughly 2 kelvins, it's increasing. Yeah. But no idea. But anyway, something happens. It's a slow dynamics occurs. T2 is increasing below 2 Kelvin.
That's probably this quantum fluctuation because with the spectrum, even gap phase would be shorter.
I see. But the temperature range is different. And one of the T1 shows a very anomaly around 10 Kelvin or something like this. But the T2 is so different. Okay. You're a theorist? You can calculate the T2 for different kinds of scenarios. Yeah. This is a very clear experimental indication of the anomaly in T2. Any other question? No? Okay, that's all.
We'll come back for the next lecture at 2 o'clock.
Very nice talk. I'm
Oh.
Sun-1. Nice to meet you. I'm a graduate student at Harvard University.
Who is the
Michel Lukin.
looking?
Yeah, Lukin. Mikhail Lukin.
Okay.
So I'm mostly doing atomic physics.
Atomic
but
physics.
as a theorist. But I'm also working with the nitrogen vacancy center.
So
Because of that, I studied a little bit on how this spin couples to the external magnetic noise. So that was one of my studies. I think it's very interesting. But you're saying this change in T2 happens at a different temperature than change in T1.
T1,
I see.
So T1 is probably the dynamics of the megahertz windows. T2 means the kilohertz windows. So it's a naive thinking is the dynamics is
And then I'm just saying
like G equivariant, like
yes,
5 Kelvin or 10 Kelvin.
so that you can include
crossing.
things like
So the characteristic is slowing down and then around 10 kelvins, maybe the frequencies is a megahertz. And then slowing down, and 2 kelvins, maybe kilohertz.
I agree. But the T2 measures the coherence. So it doesn't require energy to be absorbed or emitted. So in that sense, even if the spin liquid is gapped, it's not relevant because it's about order. But so you don't see any change in the T2 at the 10K?
No. But I have to say that the experiment stated this.
We don't know exactly why.
But there is a bias. This bias gas comes from the nuclear dipole direction. So ideally,
You have that in your
Oh wait, but you just can't.
I don't know.
you already have
But
measurements.
it's huge
That
dynamics.
encompasses you because that's the only thing
Overwhelming
you need.
change.
Second of all, your room key actually, if you have a room
What
key,
you
that
observe
is
is
also
like this.
you actually, up until